Good morning, everyone. Thank you for being here to present the recent, actually, almost a completed project we did for New Jersey demand transportation. So we are looking at a very common problem, and we try to solve it with a little bit of new method, and we try to also make cost saving and also safety improvement for duties. So basically, we are talking about asphalt pavement pothole. Try to using some preheating, so spend a few minutes before repair, and see how this can help the longevity and also the performance of the pothole repair. Xiao is a PhD student working on this project, just acknowledge him. Okay, a quick background. We all know pothole actually, it actually appears everywhere in the asphalt pavement. Basically, you're trying to avoid that, especially when you see on the highway. In this case, you have safety concern, and also it deteriorates quickly, actually, also affecting other areas. And usually it comes out with water infiltration through cracks. If you don't do very well on the crack seal, it becomes pothole, especially after freezing thaw cycles. In New Jersey, we used to have very cold winter, but recently we are getting more like cold and warm, like alternative pattern. So in this case, one day was below zero, another day actually getting warmer. So this case actually even worse for the pothole repair and also forming the pothole. So in that case, DOT is spending a lot of money to repair the pothole. And one thing is, this repair may not work very well. After a few weeks or months, you may go back and do re-repair. That's also the challenging. Another thing is, even you have to repair the pothole, you may do asphalt overlay on top of that. In this case, you also have some potential for refractive cracking. So in that point of view, if we can increase the longevity of repair, it will really save the cost and also improve efficiency. And also, if you look at the failing of the pothole repair, it may have the raveling, the edge cracking between the repair and also other areas, the depression of the patch itself, and eventually missing the patch. And in this case, we'll do the repair again. So we look at some kind of practice. Left one is, since this is 2014, look at what kind of material used for pothole. Basically, hot mix asphalt is used more common because this will give you relatively longer repair. Spray emulsion aggregator is also one way to do it, but in that case, you rely on the specific machine to do the spray. The proprietary asphalt mix is more like cold mix. In this case, actually, they're more like a combination of the modified binder and sometimes even polymer and also some cement mixed. So in that case, you can reduce the curing time for quick repair. So basically, different material has been used. And from the method's point of view, you can see here we have spray rejection. That's something I just mentioned. You kind of spray the emulsion with some small aggregate together. Full depth repair is more like if you have multiple potholes, you kind of repair it like a normal construction. You bring the vibration compactor, also bring some large machine, which is actually pretty costly. The semi-permanent sew and go and sew and roll are more like a quick repair. The difference is sew and go is you just dump in some material and then just go without any compaction. In this case, usually for emergency repair. Sew and roll are most common one. In this case, you do some quick compaction, sometimes using the truck tire, just driving on the pickup or whatever small trucks on the patching, or just use the plate compactor to do a very quick compaction. The semi-permanent one, more like you are cleaning the pothole, you also make it more like a rectangular shape, and then you do the repair. So in this case, you do more job and then try to make repair longer. So basically, based on this work, we have kind of focused more like in the boundary between the semi-permanent and the sew and roll, because this is considered as a quick repair and also has a potential for longevity. So the objective of this project was was broader, actually, was looking at different repair methods and also technologies. Actually, now we are looking at the wrap with regulator for repair. But in this presentation, we are focusing on the preheating. So we're trying to see, is that possible to do a little bit of heating before repair? And if doing so, what's the effectiveness in terms of the field and laboratory testing? And also we try to looking at, okay, what's the required heating time on the different conditions if we have different heating power or equipment available. So for preheating, actually, this is basically, we know kind of heating the pavement. It's actually not very, it's familiar to us because we are using that for in-place recycling, if you look at that. Infrared heating has been widely used. Microwave heating also has been tried. So in this case, they are using large amount of heating power to make the pavement become loose and you can mill it out. But in this case, we're trying to see, can we preheating the pothole before the patch? We just do it for a few minutes And then we hopefully in this case, we can improve the bonding between the paste patch and also surrounding pavements, because in this case, it become like a hot to hot interface instead of hot to cold interface. It's also similar to the longitudinal joint construction to try also to make the interface getting stronger. So by bringing this question, we look at, okay, there are very few studies looking at how to do the preheating, what's the standard procedure, how long, and also what's the benefits has been approved or not. So first, we look at the possible heating methods. Actually, a few DOTs have done some direct heating, so they are just using the propane heating to just use it like a torch. In this case, you have the flame, you'll be able to heating the pothole for a few seconds or a few minutes. Actually, Wisconsin have tried that. But in this case, it's not very easy to control, and also you can aging the actual material very quickly because the flame temperature can be very high. Infrared heating is pretty common, widely used for in-place recycling. So that's actually one method we're using for this project. We also look at the microwave heating. We did some trial study. It also can heat the material pretty quick, but the mechanism is different. In microwave heating, you are heating the material more like from inside the material by like a molecular excitation. So in this case, you are not just heating from the surface, which is infrared heating is doing. So if you are doing more like, let's say deep pothole or like a deep depth heating, microwave will bring some benefits. But if you're talking about shallow heating, it's not as effective as infrared. That's actually, we select infrared as this project as the first trial. Induction heating also has been used for self-heating. So in this case, you're creating the magnetic field. And if you can make the asphalt kind of partially conductive by adding some steel powder or steel fiber, in this case, you'll be able to generate the heat, the current, and also generate the heat, which basically in this case, you are requiring the repel material to be kind of conductive. So it cannot use for regular asphalt mix, actually without any conductive material like steel powder or like the other materials. So we are using infrared heating to check for this project. And then in order to make the project more like practical and also easily for like testing, we kind of using the test section instead of getting out for the real pavements, because in that case, we cannot get in course back. And also the irregular shape of the pothole makes difficult for testing. So we built a small test section at the campus. In this case, we had a 6-inch asphalt with 2 nifts, 3.5 plus 2.5. So in this case, we kind of assuming the pothole depth is 2.5 or 2-inch. And then we make an artificial pothole by putting some wood blocks after paving and also after initial compaction. So after that, we take out the wood blocks to make an artificial pothole. The purpose is try to take a course around the edges so we can do all kinds of testing. So that's basically one of the artificial pothole we made. So in that case, we conduct some trial heating. Actually, we did both infrared and microwave. As I mentioned before, microwave is kind of a little slow, already getting higher temperature inside the pavement. But in this case, the pothole is pretty like shallow. So infrared getting heating more efficient. So we also have thermocouples embedded during the construction at different depths. So in this case, we'll be able to get some temperature inside the pavement while we do preheating. And also we use the thermal camera just to get the quicker temperature actually on the surface. So here is actually one of the measurements we have. The left one is using the thermal camera, infrared camera. So in this case, you're quickly getting the surface temperature. So you can see with a few minutes, you can get a temperature increasing pretty quickly as compared to the right one, which is captured by thermocouple. So in that case, you can see the temperature still increase, but it's much actually slower. That means actually infrared heating actually has much higher efficiency actually in the surface. In this case, actually, we only have 2.5 centimeter and 5.5 centimeter depth. So actually, in this case, you can see also the difference, the shallow one getting much higher temperature. So with that, actually, also we conduct the repel. So we select different time for the preheating, and also we use one patching material. And then after patching, we did a very quick vibration compaction. It's kind of like throw and roll. So with very little compaction. And then with repair the patches, we also take the course for electric testing. We try to look at what's the interface bonding. Ideally, we want the shear bonding at the edge, but because the geometry is very difficult, so we use the bottom surface as the interface shear testing. And we use the edge surface for interface tensile. So it's still interface bonding, but it's in the tension mode. And then we use also the patch material itself for the IDT, indirect tensile strength. So the first two testing is more like indicating the phase bonding. The third one is more like for the patch material strength itself. So this will be related to more like the bonding between the patch and also the depression or the possible rotting of the patch itself. So the shear strength testing, you can just use a modified Marshall tester to do that. We didn't do confinement in this case because we really want to have a quick comparison. And also testing can be adopted by the DOT and the real field laboratory without complicated equipment to apply the confining pressure to the bonding condition. So you can see basically without heating, we even cannot take the cores actually without any damage. So when the cores are taken out, it's just debonded, the bottom surface. There's no bonding shear strength at all. And with 5 minutes and 8 minutes heating, you can see how the bonding strength will be increased. And that's expected because by preheating, basically you are facilitating the bonding and also the flow of the binder during the patching and also the quick compaction. So in that case, you have much higher bonding. And similarly, for the interface tensile, this is at the edge interface. So we're able to get the course even for without a heating case, but the strength is about like 500 kilopascal. And then with a few minutes heating, you can see how the interface tensile strength is getting much more increased, actually almost doubled after 80 minutes. This is for the patch material itself in direct tensile testing. So in this case, you can see how this IDT strength is getting increased. It's actually kind of not expected because we only preheated the pothole. We didn't actually heat the patch material. But the reason is because when you have the temperature actually increased by preheating in the surrounding pavements, even you are putting the same patching material, this heat actually getting conducted or flowed into the patch itself. So actually the facilitates or helps the compaction of the patching even only for 10 seconds, which can be proved by the air void measurements of the core, especially with the same compaction effort, air void actually going down by using preheating. So that also means in addition to the interface bonding, we also have benefits for the patch material itself. So that's for the lab testing part. But in the lab testing or field testing, we only have limited amounts of pothole. The shape is also fixed. And also the infrared heater, the power is also fixed. This one we use a 4,500 watt. In the field, maybe you can adjust the power based on the pothole size. So how these conditions are affecting the heating condition. So we started looking at we can just easily quickly develop a model to predicting all the temperature increase, and this will be able to help us decide what's the heating time requirements depending on all these conditions. So first we conduct laboratory testing, try to get a simple conductivity. Although we do have some neutral data available, but in this case, we want to emphasize actually the thermal conductivity does change with temperature. So we didn't measure the thermal conductivity at different temperatures, and we actually found there's a nonlinear relationship. So basically, you are expecting the thermal conductivity and also solid heat, both are changing with temperature. These are quite important in order to get accurate temperature prediction. And then you can build a model with boundary conditions. Basically, we consider basically normal solar radiation if we have temperature data or weather station data, and then you have a convection with the wind, which the wind velocity effects. Then you have the self-radiation, and then you have the heat flux coming from the infrared heater. So with that, we also look at the comparison of the data from the field and also model. So in this case, we do have the initial temperature actually recorded. So in that case, we use as a boundary condition, and we look at what's the comparison between the simulation and the modeling. And the accuracy is within about a few Celsius, which is acceptable. And then after that, we go back to the purpose or objective of this model is we try to looking at what's the heating time requirement, especially considering I want to reduce the heating time. So what's kind of the power I need for the infrared heater for different pothole size and also for different initial temperature. Because if you are in the cold weather, you're expecting to have more energy to basically bring the pothole to a higher temperature or same temperature. So we kind of did this sensitivity analysis, and then we try to limit, let's limit the heating time for 3 minutes. In this case, it's easier for practical implementation than what's required power for that, which actually is achievable with the current infrared heater machine. We're also looking at what's the energy consumption, because one of the criticized may come is, we are applying more energy. So from life cycle point of view, it is kind of beneficial because although you can increase the longevity, but you add more energy during the production stage. So we look at it, does that power, because higher power will make the heating efficiency higher, But in this case, also we found energy consumption is also lower to bring the temperature to the same level. So this also can help to selecting the field condition based on the different heating power we need. So quick conclusion, the infrared heater is capable to heating the edge and the bottom surface of pothole to a high temperature in a relatively short time, in a few minutes scale. And this preheating will enhance the bonding between the patching and also running pavements, which also not only to this bonding, but also increase the cohesive strength of the material itself, which is also pretty good. And then we will be able to optimize the power in order to really minimize the heating time, and then enhance the productivity of the pothole repair, because usually they just do a few minutes for per pothole in the field. And then we are planning to have a field study. So in that case, we'll use the preheating. We'll do it in the field. We'll look at it just what's the life cycle span for different measures, and then we can have a full life cycle cost evaluation. Finally, just want to acknowledge the financial support by New Jersey Department of Transportation and also Rutgers Case Laboratory. Thank you.
I'm the next presenter, so it's okay. It's just eating into my time. Thanks, Hao. Great presentation. So one thing we noticed when we do the synthesis, like the most maybe critical thing, and this question has two parts. Maybe the most critical thing is always the density, right? Because you don't want water to infiltrate and create potholes. Did you do any density check to see if the preheating? I'm assuming the cohesive strength is probably a function of that density, but did you do any density check to ensure that?
I think we happen to have some measurements on the left.
Okay, I missed that. Yeah, okay, perfect. So that's exactly what we expected. And the second question, you use vibratory compaction. So when we interviewed kind of the districts in Illinois, they don't like to use vibratory compaction because most of those are owned by contractors. The DOT doesn't own enough of their contractors. So do you think what they do when they do throw and roll is just basically compact with the truck tire from the traffic attenuation vehicle? Do you think that's a possibility, like, or because you're preheating, does the binder kind of get in the tires and create a problem with the rubber tire?
That's a very good question. So we did think about it. Should we just use the truck tire for compaction in the test section? We kind of choose the vibrator compactor is we want to be more uniform to see the comparison. In the field, we will do the battery truck tire we are doing. My guess is the trend will be there, but the value may change. As far as this, whatever the material will be kind of adhere to the truck tire issue, I think this will be minimum because we are just preheating the pothole. So actually the bottom material is not getting that much heat. It just have some heat which helps the compaction, but surface is basically not a very high temperature. So I'm not worried about that. Yeah.
Okay.